Thank you. Before we start, quick questions. Before this talk, who knew what was SD for? Raise your hand. All right. Yeah, 10 people. And who owns an SD card or a micro SD card? Quite easy. Good. So who am I? As in the presentation, I'm working in Switzerland for Kudelski Security. I'm in the R&D department. I'm doing hardware stuff, embedded devices. I'm also part of the organization of a security conference in Switzerland called Black Alps. I have some stickers with me if you like. Just come and talk to me. And I'm also developing HydraBus. This is a tool that I will show you. I might try to convince you to get one. You will see that during the talk. And also I have stickers with me. So yeah, just come by. So basically, SD is for secure digital. So once you know that, the next question is, so secure, why is it secure exactly? So we will see what are the security features that are in SD cards, also some vulnerabilities that I found. One thing to remember is I'm trying to keep those attacks as low cost and easy to replicate as possible. So since most of you have SD cards, you might be able to replicate those tests and try for yourself to find those vulnerabilities as well. So what's an SD card? Basically, it's just a microcontroller interfacing the SD interface to an embedded flash memory. For more information, there was a huge talk by Bunny and Xobs at the CCC, where they went into the cards, decapping them, showing how the microcontroller works, how the flash is working inside, etc. That's a really good talk. There are three main ways to communicate with an SD card. The first one is the most classic one, is the SPI bus. So you can use the classic SPI, which is mainly used, for instance, by Arduinos. Or you have what they call UHS-1 or SDIO. It's a quite faster bus that uses more data lines, up to 4 of them. And the more recent communication protocol is called UHS-2, which is even faster. I don't have the numbers there. And the card has way more contacts, as you can see. This is a UHS-2 card. But most of the time, what we will see in the card is just one row, and this is usually just UHS-1 or SPI. So, if you want to know exactly how it works, the best thing to do is to find documentation, specs, etc. They are available on sdcard.org. You can get the what they call the general simplified specs. This is the first part. It's 260-ish documents with all information about the physical size of the card, how the commands should be sent, what are the responses that you get, etc., etc. For instance, this is the way to initialize a card. I won't go into the details, but you can see that it's quite messy. It's quite a messy protocol. So you have different possibilities depending on the response of the card. It might be a more recent one, so you have to send other commands. It's not really easy to understand, but you need to sort it out. What the documentation explains is that the protocol is basically a query and response protocol. So you send a command. This command has a specific ID and a specific function. When you send this command, you can send some arguments with it. Then you have to send a CRC, so the packet is valid. And then the card will reply to you with the response of your main command. Because this protocol is really not easy, there are 7 different response formats, depending on the command. So every time you need to implement a new command to see exactly how it works, you have to then find out which kind of response it is, its size, the data that is inside, etc. So yeah, it's kind of difficult protocol to play with. There's also what they call a block transfer feature, because as I said, the usual size is 4 bytes for the argument of a command, which is not enough. So what they do is you can send blocks, data blocks. So you start by sending a byte 0xFE, then as much data as you want, then a CRC. The length of the block is defined by a specific command, so you can send a command to shorten or make a bigger block of data, but by default is 512 bytes. So to interface with an SD card, I used the easiest solution. I used SPI because it's quite easy to find tools that are using SPI. It's also easy to script with Python, and it was supported by HydraBus. Told you it was a really good tool. What is HydraBus exactly? Basically, it's like a bus pirate, but a more modern version supporting more protocols. It's also fully open source. Good stuff. So my main setup was basically an HydraBus with the SPI interface connecting to an SD connector. So it was not the worst part. Then I started sending commands to the SD cards, getting some response, failed a lot. And all in all, I added more features, more commands, understood exactly how it works. So I mainly created a small tool that is a way to interact more easily with SD cards. One fun thing is that, as I said, all the queries and the response contains a CRC. In the specs, it said that this CRC is optional. So you can just send zero instead of the CRC, and most of the cards do accept the commands, except some manufacturers that want the CRC to be in place. So depending on the cards, you don't have the same results. Again, really easy stuff. So I can show this. So basically, the tool is a CLI interface. You can type init to make the initialization of the card. You remember the big graph. Basically, this command does everything for you, which is way easier. You can directly query some information from the SD card. So here I'm querying the identification register, which is basically this huge value there. And then I'm also parsing the data within it. So you can extract information and get a more readable results. Same goes for the card physical properties, its size, the block size, every information. So you get this huge blob there, and some bits do contain this specific information. So the tool does everything for you. So it's way easier to interact with SD cards. So now that we are able to communicate with the cards, next part is to do a Control F on the on the specs and look for security or something like this. There is a small chapter within the first document in the specs that basically says that all the security features called SDMI are for content protection, for music or movies and stuff like this. And this is only available for paid customers after signing NDAs and in the file which is called SD Specs Part 3. So, unfortunately, it's not available, so this talk won't be about those specific features. But in the case you don't want to pay SD or whatever, you can ask Google, and it will it has indexed the specs, so you are able to get it anyway. So, looking again at the specs, there are two main ways to protect content from the card. The first one is a write protect bit that you can set directly on the card, and another command which is called the CMD42 to set a password on the card. Basically, you can put a read password on the card, and you cannot read anything from the card unless you have given the correct password. Fun fact, it's mandatory for all the cards to accept those commands and implement them. to get the SD label. So all the cards you can find usually have those commands, even if they are not used. So this CMD42 is called also lock unlock. Basically, it's a way to set a password of up to 16 bytes. It's not limited to ASCII characters, so the key space is quite huge, not easy to brute force. And how it works is you send this CMD42 commands, and it would be too easy to set the parameters directly in this field. So you have just to send this command 42 with null bytes as data and CRC, then send a block containing all the parameters. So basically your block should contain the start, which is in the protocol configuration. Then you have a whole byte containing special flags within these bits. Then the password length, which is encoded in 1 byte. Then your password and the CRC if the cards need it, otherwise you can just set to 0. So all those options there, here we have the set bit, basically it's to set a new password, the clear bit to remove the password, the lock bit is to actually lock or unlock the card, the erase is basically if you forgot your password, you can use the erase bit to wipe the card, and it will wipe all data and the password as well. So I started to play with that, sending commands to lock the card. So basically you send this block, you set the set bit. Actually you can also in one shot use the set and lock bit. So once you put the password, the card is locked right away. And then to read the lock status, you need to read its status register, which is usually the CMD13, but in my tool you can just type status and you get the card status as well. Once the card is locked, to unlock it, you need to first initialize the card, then send this CMD42 command. Then in the data block, you need to set the lock bit to 0, so it means unlock. Then the password length, then the password, then the CRC, send it. Then the card will process your password, then reply with either the correct status or password failed status. So now the juicy part. As I said, the card will pull down the data line while it's processing the password, so no other commands can be sent during the password check. So what happens if I show you here? You can see this is a logic analyzer output. So basically you can see the status of the clock line, of the line from the card to the Hydra bus, and from the Hydra bus to the card. So here you see that I'm sending this CMD42 command. Then I'm sending this password block here. And then the card starts processing it by pulling the line to 0. And then I have my response. But if I try to zoom in a bit in this part on the right, you can see that my password was 123456. Great password. So here you can see that if I send a password length, a password which contains 5 zeros, it takes around 53 microseconds to process my password. If I type 6 characters, which is the same as the length of my correct password, the time to process is 55 microseconds. So what's interesting here is that the card controller basically first checks for the password length, and then it processes the password byte per byte. And as soon as there's a discrepancy, it will answer with a password is incorrect. So basically, we are able to, if we are looking at the time used to process the password, we can guess the length of the password, then we can guess every byte one by one until we get the full password. So that's good. It's just a bit complicated to measure every time for every byte possible. So I tried to look for a way to automate this part. So what I did was basically that since I'm controlling the SPI interface, as soon as I finish sending my block containing the password, I'll try to read data as fast as I can. So what I will read is basically nothing useful, but I will read all the zeros coming from the card, right? So if I'm reading as fast as I can then count the number of zeros I read, and this will give me the time it took to the card for being able to process my password. So in practice, how does it look like? So I still have my card here. So I will lock it with a super secure password. If I try to read the status of this card, it is locked. So if I try to read, let's say page 0, it's not possible. The card is locked, cannot do anything. So what I will do is basically use this function to test for the length of the password. And what you can see here is that when I send a command with a length of 0 to unlock the card, I was able to read 122 zeros before the card tells me that the password is not correct. For a length of 1, might be a bug there, sorry. For a length of 2, it's 124, 24, 24, and then at the length of 6, it's just a bit more than it was previously. So by doing this a lot of different times, sending, let's say, okay, so my password now that I know it's 6, I will try to send 6 times 0, get the response, then first byte is 1, then all the others 0, and for every combination I will get that and get the maximum length, so the correct value, so I will know the correct password. To give you a demo, I can now run this brute force tool, and what it will do is get the length, and then it will show me the password for every byte that I was able to get. And this final password is then the one I set, 1, 2, 3, 4, 5, 6. And if I try to read the card, I'm able to get the data. So I was lucky enough to make it work with the card I had. So what I did was buy a lot of different cards to get cards from different manufacturers, different sizes, if there was a difference between an SD card or a micro SD card. So bought a lot of them, around 20. And I also asked friends, telling them, don't worry, your card will be fine. Guess what happens? The only card that I was able to lock but not unlock anymore was a friend of mine. So, too bad. So all the cards, I got them. First, I had to make them work correctly because, as I said, the protocol is not that specific on some things. As I said, there are cards that will require the CRC, some others don't. So I had to find some workarounds for some cards. But once I have everything working, I locked them all with 1, 2, 3, 4, 5, 6 as a password. Then tried my timing attack on it to see the results. It was working quite well. And I had also some special cases that I found that cards basically don't follow exactly the specs, but you have some things. For instance, an SD card from Somni that I bought basically does not answer anymore after 3 failed attempts. That's a good thing. So you should remove the card, put it back again, and then you have 3 more attempts. Thing is, you can just send the reset command, which is cmd0, and then you get 3 more tries. So you can just, it just takes a bit more time because you have to send this reset command every 3 tries, but it works exactly the same. Again, on a Sony micro SD card, I was not able to read any 0 bits. It was really checking the password really fast. So I was thinking, well, maybe there's no vulnerability there. Then I started thinking, okay, so I have my SPI interface, which basically pulls the lines at 42 megahertz. I also added a logic analyzer, so I can go as much as 100 million samples per second. And I still didn't have any results. So here I cheated a bit. I went to to my colleague's lab and borrowed their oscilloscope, which is 40 gigasamples per second, which is a lot. And what I'm able to see now is this is basically the processing time for the SD card. And there you can see that if the password is 5 characters, 6, 5, 6. So there's really a really slight difference, but you can still see them. But unfortunately, you have to get a huge oscilloscope to see that. Another special case that I found is on a Kingston SD card, where I was able to find, using the timing attack, the password length, but then I couldn't use the timing attack to get the password. So I did a lot of different stuff, and I found this. So again, I took the huge oscilloscope just to be sure that there was nothing. So when I set 5 characters password, this is it. With 6, I can clearly see the timing change, so that's great. But then if I set the first correct byte, you see no difference. With 2 correct bytes, no difference. 3, still nothing. 4, you start to see an increase. Why is that? To me, it's because the card checks the password 4 bytes by 4 bytes. So it might be a 32-bit microcontroller within it, and it's checking the 32 bits at a time. So it's just a bit longer, but it's still possible to do the timing attack. But instead of every byte, you have to brute force on 32 bits. So this is my results that I had. So basically, all the cards there are vulnerable, except the ones from SanDisk. One important thing to note is that the card vendor is not related to the card manufacturer. Basically, there are OEMs that produce the SD cards, and then they sell them to, I don't know, Sony, Kingston, SanDisk, for instance, and they're rebranded to their own name. So what's important there is not this column name, it's the manufacturer name that is important. So as I said, I found all the cards from Tencent, Phison, Sony. This one I don't know who it is because it's not written. There's no list of the vendors on the SD website. And the only card I found that was not vulnerable is the SanDisk one. A funny thing is that the Samsung card I have, when I send this CMD42 command, basically the card responds to me that this is an invalid command, it does not exist. So I don't know how they get the SD logo, but whatever. So once I found this one, it was already cool, but I was wanting to go a bit further. So I took the second security feature, which is the write lock mechanism, and in my theory, I was, okay, so maybe if I set the right protection on the SD card, and then I ask the card to remove the password, maybe it will remove the password, but not overwrite the flash, right? This is an idea, so let's try to see how it works. So I write some data on the card, set the right protection, set the password, then I power cycle the card, try to clear the password, so it should remove the password and all data included in the SD card. And if I'm able to read something back, that means that this feature has not been implemented correctly, right? Fortunately, all the cards I tested did a good job. They basically followed what is written in the specs, which is written there. Similarly, the card shall keep temporary and group write protection during the erase execution and clear write protection after the erase of all data is completed. So they're doing a great job. That's cool. But there's one different thing that I also wanted to check is basically when you send this clear password command, what is the card doing first? First erasing the data or first removing the password? Because if it's removing the password first, that means that if I remove the card at the right moment, I'm able to get a card with no password protection anymore, but still the data inside. Sounds a good idea, but how do I do it? I mean, it's not that easy to, let's say, press enter, then pull out the card. There's another way to do it. Basically, how the card works, it's using flash memory. So to write data on flash memory, it requires a lot of power, right? So this power has to come from somewhere. So within the flash memory, there's a mechanism called charge pump, where basically it pulls a lot of energy, then send it once to the card to set all the bits to a 0 or to a 1. So in theory, I should be able to detect an increase in the power consumption of the card just before it's being written. So if I can detect this, I might be able to shut down the card. So how do I detect an increase of consumption? I have to measure the current going through the SD card. So you take your electronics 101, Ohm's law, tension, current, resistance. So basically, if you had a really small resistance on the travel between the SD card and the ground, you can see that if the current is rising, the tension around the resistor will also increase. So we should be able to actually see that the card is consuming more power. For you at home, if you don't have small resistors, if you vape, you are able to build a really small resistor with your vape material. It works. So I set up my card. Again, I put this small resistor just after the card. And then I used a small oscilloscope to see if I can see some data. So here on the yellow line, what you see is basically the tension to the near the resistance. So this value is proportional to the power consumption of the card. So when I initialize the card, you can see there's a small spike there. Then it's doing some fancy stuff here. So we're able to see something. That's a good part. By the way, checking the password also consumes some power. So using this, I'm able to as well see the power consumption of the card during the test. So if I have 5 characters, 6 characters, you can see an increase. Whoop, around here, you can see an increase there. And then if I try to set the good passwords, it's also a bit more. So this is another way to actually get the password using the timing attack, but by looking at the card's consumption and not on the protocol. So this is good. I'm able to get some data. That's fine. But then my question is, how do I take this value and use it as a trigger to remove the card, right? So I tried to look for all the tools I had, and it looks like that's the STM32 ADC, which is the analog to digital converter. In the STM32, there's a feature called the watchdog, where basically you can set a lower and upper boundary. And if the value read from the ADC goes above or below those thresholds, it will trigger some feature, whatever. So fortunately, the STM32 is the main component of the Hydra bus. Told you it was a good tool. So what I did, I added this feature, the ADC trigger. So I'm able to set the thresholds. I'm able to change the delay. The minimal delay is 1 microsecond for the microcontroller to work. So once I have this trigger, that's the first thing. But then what do I do with this trigger? I mean, I cannot use it to, let's say, use a motor or whatever to pull the card out, right? So what you can use is use what is called a MOSFET. A MOSFET is basically a transistor, but is driving using tension and not current. So basically, when you apply tension, it will let the current flow through the MOSFET, and if you don't put current, it will block. Basically, so it's a switch that you can drive with a GPIO. It's also, if you're on a tight budget, if you have old motherboards at home, you have a lot of MOSFETs on it, so you can unsolder them and use them, for instance, for this kind of project. So, if you mix everything together, what you have is your SD card there, you have, no, other way around, there. So you have the SPI interface here, you have the tension coming here, this is the ground, so it goes there to the MOSFET, the MOSFET is triggered by my trigger that I created. Then after the MOSFET, I have my probe for the power consumption, then my small resistor there, then finally the ground. So the circuit is basically you have your 3.3 volts coming here, the card is processing the information, then the current will flow there. If the GPIO is to 0, the MOSFET will block the current, so the card will be off. And if the GPIO here is to a logical 1, the current will flow, so the card will work. In practice, it looks like this. It's a bit messy, but you can see there the resistor is around here. You have the MOSFET, which is here. This is the hydra bus I use as an ADC trigger. This is the SD card interface. This is the hydra bus I use as an SPI interface. This is a small power supply. And this is the oscilloscope. So my setup is finished. I should be able to start and see if my initial assumption was correct. So what I will do now is write some data on the SD card, set a password, just power cycle the card once just to have it perfectly stuck. Then send the clear password command, but with the trigger enabled. So as soon as there's a flash write, it will cut the card, then reboot the card and see if there is still data and if the password has been removed. So in practice, how does it look like? Here it's on a card. You can see that if I send this clear command, you can see that the consumption is increasing. Then there's a spike here, and then there's the flash erasing process, and then the card is clean up. In blue, this is the trigger line. So once I set up and enable the trigger, what you see is basically exactly the same at the beginning. And once there's a spike in consumption, the trigger will fire. Then the MOSFET will will block the current. So the card will be shut off. So you can see that as soon as the trigger is going, the consumption is nearly equal to 0. On another card, this is another example. So visually, you can see that it looks like it's working. So the main question is that, was it vulnerable? The answer is yes. And the bad thing is that in the specs, it's written that the card shall keep its locked state during the erase execution and change it to the unlocked state after the erase of all user data. It's unfortunately not true, so to me it's a fail. And to show you how it works, I have a demo video that I can show you, and we'll try to comment it live, if it's possible. So on the right here, we have the hydra bus that is doing the triggering stuff. Yeah, it's a bit small, sorry, but the fun part is this one. In the middle, you have my SD tool that will basically send the clear command to the card. And on the right, you have the output of the oscilloscope. So here, I'm starting the card. I just send the init command so you can see an increase of consumption here. Now I will set up the trigger. So everything looks good. Now I type the remove command, which basically sends the remove password command to the card. And what you see is that there is this increased consumption, then the spike, and right at this moment I will pull the GPIO off to stop the card from working. So now on the right, what I will do is just enable the MOSFET again. And if I try to initialize the card, my program crashed because the card was not responding anymore. This can happen. So you will see on the left that I will physically remove and reinsert the card. So you will see something happening. I run my tool again, initialize the card, check the status, card is unlocked, good point. And if I try to read some data, for instance from the first page, the data is still here. So I tested this on all the SD cards I had. Unfortunately, I had one card that died during the glitching process, so I don't know if it was vulnerable or not. Otherwise, nearly all the previous cards were still vulnerable, except this one, and the SanDisk were not vulnerable as well. So SanDisk is still doing a good job as respecting what is written in the specs. All the others, a bit less. So in conclusions, it might be a useless vulnerability because this feature is not used by any operating system. So if you have a locked card and you put it in a Windows, OS X, Android or whatever, it won't see the card. That's it. So unfortunately, it's not that used, but it's present on nearly all the cards. It affects a lot of manufacturers. So it's quite common to find a vulnerable card. Reading the specs is really fun. You sometimes have to read those things, and yeah, you have good stuff inside it. Also, even if it's written in the specs, that might not be true, as we saw that the specs say that you have to remove the content of the card before the password. It's not the case. So even if it's written, you have to test it just to make sure that it works correctly. Also, as you can see, using side channel analysis is not that difficult. You just have to take a bit time, try to fiddle by yourself, find some components, and you should be able to basically redo exactly what I did. The tools are evolving, their price is getting lower, so it's even easier today to have tools doing side channel analysis. Also, automation is really important. Because when you have to test a lot of cards, you have to run a lot of commands, you have to check for timings, etc. It can take really long time. So if you can automate as much as you can, it's something that you can just run, then do something else, then come back on the next day or some hours later, get the results, and you're good to go. I might have modified a bit this XKCD, but basically it's the same idea. On a future work, there's a new feature in the specs version 5, which went out in 2016. And this feature is called COP for Content Owner Protection. Basically, it's a password to protect the password remove. Why not? I didn't find a card that supports this COP feature, so unfortunately I was not able to test it and see if it was also vulnerable to, let's say, a timing attack or whatever. And that's pretty much it. Thank you very much.
Hi, thanks for the presentation. I really enjoyed it. And I have a question, like for the example, for the Samsung card, yeah, that doesn't support SIMD42. Maybe have you tried to mess with the controller itself to send like undocumented or unexpected comments? Because if it doesn't support what is in the specs, maybe it has some like proprietary comments or other stuff.
There are proprietary commands. If you look at the CCC talk I mentioned earlier, they show a lot of things they can do with manufacturer commands. Thing is, on the Samsung card, it's basically this is a standard response from the protocol, and the bit saying that it's unimplemented command is set. So basically, the card is just responding as expected, but that's this command is not available.
Okay, thanks.
Hi, thanks a lot for the talk. Oh, sorry. There are a couple of micro SD cards that have a secure element on them and are like really high security SD cards. Have you ever had a look at them?
No.
All right.
No, I just took cards that I found in shops. That's it.
You had two Sony cards, one that was vulnerable, one that was not. Is there any chance that one of them was a counterfeit card? And certainly Bunny found an enormous number of SD cards that were branded and with mainstream manufacturers, but were actually just ghost shifts or other counterfeits.
As I did not understand the question.
So you had two Sony cards in your table, one that was vulnerable, one that was not. Did you open them up or decap them to see if one of them was a legit Sony card or if they were both legit?
Not at all. No. The purpose was basically to do stuff that everybody at home can do. So I did not go the next mile. Maybe in a future research, but not yet.
Hello. What about disclosure?
I didn't do any disclosure, to be honest. Because in any case, I won't see how they would patch that. Because I've never seen a firmware update for an SD card. So, no, unfortunately, I did not do any disclosure.
Thank you for the presentation. I just want to ask you regarding the time for the brute force attack. You say that you just try 6 characters. Have you tried the whole 16 characters and you see the time difference?
Yeah, it's just a bit longer, of course. But
in seconds, minutes?
Minutes. A matter of minutes.
Thank you.
I have a question about the brute force attack on the password. You switch technique and you use an oscilloscope when you don't have the resolution to do your timing attack using the SPI. Would it be different through the other interface, which might be faster?
It could. Well, then the card might not support higher SPI clock rates, so this might also be variable. But in theory, yes, if you have a faster SPI interface, you would be able to get more precise results.
So the other ones, I don't remember the name, but you said you can speak SPI and also...
Oh, yeah, the other protocol is SDIO, which basically it's...
Would it be fast enough?
It should, but in that case, you won't be able... depending on the SDIO controller you have, you might not be able to make it read dummy data like this.
All right.
So it's really easy to do using SPI because it's a raw protocol. If you have a SDIO controller, you might just be able to ask him to send this specific command and get your data back. So maybe not.
So I think all the SD card you checked are older than maybe 6 years or 7 years.
Basically, I bought them. It was in I would say February or March. The date that is written here, it's the production date. It's I would say that it's a value that is stored within the card. So I don't know if it's in a mask ROM, for instance, so it's always the same, even if it has been produced, let's say last year.
So didn't you see any newer SD cards showed in the production date?
No, it's even I think this 128 gig. It's the most recent I think I bought. And even there, the date is still 2012. So I wouldn't let's say I wouldn't be surprised if this data is just the initial production start date, and it's never changing even if the card is produced years later.
Nice.
Thank you, Nicolas. Thank you.
Thanks again.